Well, things get a little more complicated if we are not able to find m linearly independent eigenvectors associated with an eigenvalue of multiplicity m. So here's what happens. It'd be nice if we could proceed as we did in the repeated characteristic value for the second order linear differential equation with constant coefficients, like as in unit 3 lesson 2, where we just multiplied our extra solution by t in the double root case. Remember that? So we could then assume a second solution of the form C2 times t times eigenvector k times eigenvalue lambda with multiplicity, let's say 2 even. And so if we assumed a system like that and checked out the Wronskian of our attempt at a second solution by just multiplying our first solution by t, we got problems because the Wronskian of those two solutions is unfortunate. If you factored out the e to lambda t, k1, k2, and tk1, tk2, and if you multiply that out, you get e to lambda t times k1, k2, t minus k1, k2, t, and the problem with that is it's 0. So even though it's a great idea, it doesn't work. The fact that it doesn't work means we got to try something else.
I'm ready, so let's go.
Okay, well, here's what you have to think about. We do, in fact, multiply by a t, but then we still must come up with another vector, and that vector has to be associated with this particular solution, and it's not as crazy as it seems. So we'll try a second solution of the form x2 is k, our eigenvector that we found, times e to lambda t times t plus some other vector which we're going to search for, times e to lambda t. So if we take this and substitute into our original homogeneous equation, that means if this is our x2, then we're going to take the derivative of it, and that would be from the product rule on this part, first d second plus second d first, k times t times lambda times e to the lambda t. That's the first d second part. And here's the second d first, that's just e to lambda t. Plus, well, the derivative of this is just lambda times e to lambda t times our vector p. And then a times this vector, right, is going to be on the right-hand side. And then I took the time and trouble to subtract this one and this one from both sides. So we have a times the solution vector minus this equals the 0 vector, or written another way, carefully. Take all the terms with the t times e to lambda t in it, and that would be this one and this one, and factor out the t times e to lambda t. So there's that part of it. And then take the terms that don't have a t, e to lambda t, so a times vector p times e to lambda t, and this one negative k times e to lambda t, and this one negative p lambda times e to lambda t. So then we would have written like this equation. Well, since this is true for all t, we get two equations. In other words, whatever value t is, then we know that a minus lambda I, because look, that's what this is, times k equals 0, because there's a 0 on this side. Actually, that should be a 0 vector. There. Nope. There. Okay. And so that means there can't be a t e to lambda t, and there also can't be a lambda e to lambda t. And if that's the case, then we've got the fact that this is 0, but we already got an eigenvalue and an eigenvector associated with it. But now here's where we get our other eigenvector, or our other vector we're going to use as an eigenvector. This also has to be 0. So therefore, a minus lambda times I times the vector p has to be equal to k. See? Since this has to be 0, then this must be true. So we already got this done. We already got our associated eigenvector k, the one associated with lambda. Remember, the problem is lambda had multiplicity that was higher, and we needed another eigenvector. So we can now solve this equation for p, and then we have a second linearly independent solution associated with lambda. Here is an example. Next video.